Hello everyone, this is Dr. Rajesh and today I am again with you with my next video lecture. In this video lecture, we will study how to verify Gauss divergence theorem. In the earlier video, we have made the use of divergence theorem to evaluate the surface integral. But now here the question is to verify Gauss divergence theorem. So we have to verify it and see how we'll do it. So let me first write the Gauss divergence theorem. That what does Gauss divergence theorem gives? This is the statement of Gauss divergence theorem. Gauss divergence theorem ds is equal to volume integral of divergence of vector field F over the region R. So this we have to verify. Say this is equation number 1. We have to calculate and this is over the surface S. So now we have to calculate this one. From the earlier video we have calculated this volume integral and that was equal to, so we will not be evaluating it again, we have already evaluated it from the earlier video. We have evaluated it to be equal to this triple integral was equal to this triple integral divergence of F over the region R was equal to A B C and inside was A plus B plus C. So this was the volume integral that we have calculated in the earlier video. So now we will try to calculate the this left hand side, the surface integral. Before calculating the surface integral, we will try to understand the concept of projection. Let us say these are the rectangular axis. Say this is O, this is X, this is Y, and this is Z. And we have some surface. Say this is the surface, and upon this surface we have a small infinitesimally small surface, and that surface is ds, and this is the normal to the surface. So if we have to take the projection of this small surface element in the xy plane, so what we'll be doing, we will be projecting it in the xy plane. So this is the projection in xy plane. Say this is the projection, and it will be having area which will be given by dx and dy. So now if we have to see how this projection is done in xy plane, so for that we know that if we could find the angle between the surfaces, then ds cos of that angle will give the projected surface in xy plane. But we know that angle between the surfaces is equal to angle between their normals. So this normal to this surface is this one, and normal to xy plane is z axis. So if I say that k cap is the unit normal along z axis and j cap is unit normal along y axis and I cap along x axis. So if we have to see the angle between this surface ds and this dx dy, we have to find the angle between the surfaces. So as to find the angle between the surfaces, we will find the angle between their normals. So normal along the z axis is this z-axis is normal, so normal is given by this unit vector. So if I retrace it, say this is the normal along z-axis and this is the normal to the surface, and say that angle between them is gamma, is gamma. So if I say that, what will be the projection? Projection in xy plane dx dy. Why we have taken dx dy? Because this element is infinitesimally small in xy plane. This will be approximated as a rectangle because it is infinitesimally small. So therefore I have taken here dx dy. So this will be equal to ds cos of gamma, ds cos of gamma. So this implies that ds is equal to dx dy divided by cos of gamma, and here from here we know that k dot n cap is equal to k cap magnitude into n cap magnitude and cos of gamma using the formula for dot product, and we know that these are unit vectors, so their magnitude will be 1. So this will be k cap dot n cap is equal to cos of gamma. Since this surface is laying in the first octant only, therefore the angle cannot be greater than pi by 2. So therefore if I say this cannot be greater than pi by 2, so this cos gamma has to be positive, and if this has to be positive, then this k dot n cap, that mode has to be taken. So this is the value. So if I substitute this value over here, so this will give dx dy divided by, it will be k cap dot n cap and its magnitude. So this is the surface area when this surface ds will be projected in xy plane. So this will be the formula when this will be projected, and it can only be because it is area. So this can be projected, not a volume. So this is surface area. So this can be projected only in either of the three planes, either in this plane, or in the plane that is zy plane. So similarly we can determine the formula for other two planes also, and if I write it on the same lines, then it will be, this is in xy plane. Similarly, in now if I project it this in z x, what it will be in zx, it will, or it and yz. So firstly I am projecting it in yz. So it in yz, we will be getting ds will be equal to yz means dy dz, fine, and it will be cos of alpha. If we see the angle, say this is the unit direction of unit normal along x-axis, this is the direction of n cap, this is n cap. So this angle is alpha. If it is greater than pi by 2, so we will take its mode. So this will be alpha. Okay, so now this will be further equal to, this will be equal to, here will be dy dz, and angles between I cap, which is normal to zy plane, and this is I cap and n cap. So this will be I cap dot n cap. Its mode means it will be taken positive. So this will projection in yz plane. So similarly in zx plane, what will happen? So where is zx plane? This is zx plane. So this will be projected something like that in this plane. So it will be projected, if we say, it will be projected something like that over here. It will be projected something like that. So in zx plane, what is the normal direction of the normal to zx plane? It is a j cap. So if I see what will be the angle, say this is the j cap, and this is the direction of the normal n cap. So this angle is, say, beta, is beta. So this will be, in this case, ds will be equal to dz dx divided by cos of beta, and this is further equal to dz dx divided by, it will be, and this is your j cap, it will be j dot n cap, this one. So this is the projection in zx plane. Now we will come back to our question. So, and we will be making use of these three formulae that we have just discussed, this one and this one. This is for projection in xy plane, this is for projection in yz plane, and this is for projection in zx plane. So now let me come back to the question, and question is, see, we have to calculate the this surface integral we have to calculate, and this is the vector field given. Okay, so we have to calculate this. So this is the vector field, so I'm going to calculate this surface integral. Okay, so let us draw the parallelepiped again here. So I'm going to draw the parallelepiped over here. So this is the parallelepiped, and these are the rectangular axes. Say this is x-axis, this is origin O, this is y-axis, this is z-axis. So I have drawn the parallelepiped and name it as A, B, C, D, E, F, and this is G. So I have named the parallelepiped. It has 6 faces. The face number 1 and opposite to that, this face opposite to that, and this face and this face. So we will be writing these faces. So if I say that this surface integral consists of 6 faces, therefore we will write this surface integral as sum of surface integral over these 6 faces. So let us write it, and this will be something like this one here. Oh, I'm going to write the 6 faces, the nomenclature of these 6 faces. So I will write it symmetrically. Don't write it randomly. I am going to write it symmetrically. First, I will be writing, say, these two faces. Say these faces and this face. So these faces are, I'm going to write O, G, F, E, and next will be A anti-clockwise sense. A, B, C, D. A, B, C, D. Now write down this face. This face. Okay, so it will be, and in anti-clockwise signs, A, O, E, D. This will be B, G, F, C. Now next will be this face. This and the topmost, bottom and the top. So I'm going to name it as A, B. This is uh, A, B, G, O. A, B, G, O, and upper face is C, F, E, D. So these are the nomenclature of 6 faces. Now if we further see this OGFE, OGFE is ZY plane, and so if I write it over here, this is ZY plane, ZY plane, and here in ZY plane, if you see here x is 0. In ZY plane, this is present at this point, and here x is 0. So if I say here x is 0, so I am noting down these parameters. You also have to note down in the exam also. And this is A, B, C, D is also ZY plane, is also ZY plane. This is also ZY plane. And here, if I say x is equal to A, so these are the parameters. And if we say what will be the unit normal in these phases, like if we say this phase, outward unit normal will be outward unit normal will be along this direction, and this direction will be outward. We have to take the normal outward to the parallelepiped. So this will be a n cap is equal to, and we know this is the positive x-axis and this is in the uh, opposite direction. So this will be, instead of I cap, it will be minus of I cap. So if I say over this phase n cap is equal to minus I cap, and over this particular phase the outward unit normal will be like this, it will be like that, and it will be n cap is equal to I cap. So if I write here n cap will be I cap. So these are the two planes that we have dealt, and we have written both were the zy plane, we have written them together. So these are the two parameters. Now next move to AOED. AOED. This is Z X plane. So in ZX plane, if I say Y0, so if I write this is Z X plane, it is Z X plane, and here Y is 0. Y is 0, and if we see what will be the outward unit normal, outward unit normal will be in this direction, and if I say this will be in this particular direction, this will be n cap is equal to minus j cap, because j cap will be something like in the positive increasing direction, so it will be opposite, so this will be minus j cap. So if I write here n cap is equal to minus j cap. Similarly, this is also zx plane, so this is BGFC. So this is BGFC. So in this case, unit normal will be this one. This is n cap is equal to j cap. So here will be n cap is equal to j cap, and this plane is present at a distance y is equal to b. So here, if I say y will be y is equal to b. So now come back to this next plane, and this plane is ABGO. ABGO. So in this plane, the outward unit normal will be in this direction. So this will be, this along this direction is k cap. This is k cap and this is opposite. So n cap is equal to opposite of minus opposite of k cap. So this is minus k cap. So if I say that this is xy plane, and the here n cap is equal to minus k cap, and if I say in this xy plane z is 0, so z is equal to 0 over here. So now for the third one is this one. In this, if you draw the normal, so this will be n cap is equal to k cap. So this will be, this is again xy plane, and here z is equal to c. So this distance is c. This distance is c. So you can say that this distance is c, and n cap here will be k cap, and this distance is b, and that distance is a. So these are the distances, and I have written all the parameters. So now we will be making use of these parameters. Now we see that we can write this integral as like this. Some of these six integrals I have written. Now we know that this is zy plane, so this will be, uh, it is zy plane, so it will be dy dz, and this is also zy plane, this will be dy. And now see, here, this plane is xz plane or zx plane, this is also, so here will be dx dz, here will be dx dz, and now these are xy planes, xy, so here will be dx dy dx dy, and in place of n cap I'm going to substitute here the corresponding values. This is minus I cap, here will be I cap, and so on. So I'm going to put these values, and it will be something like this one. Here I have placed the value at place of n cap as minus I cap, and in this it is I cap, here is I cap, here is minus j cap, here is minus j cap, here is j cap, here is j cap, this is minus k cap, there is minus k cap, there is a k cap. So that I have done. So now I am again going to recall the projection formulae that we have done. So these are the projection formulae that we have done. I am again going to write over here. So these are the projection formulae that we will be using. So here see, this is yz plane. So yz, for yz plane it is I cap dot n cap. So if I write over here, this will be uh, this formulae, this one I cap, and our n cap is minus I cap. So here I will be writing I cap dot minus I cap. Similarly for yz, it will be I cap dot n cap is I cap, and for xz plane, for xz plane, where is that? This is xz plane. It is j dot n cap. J is will be there for xz. It will be divided by j dot n cap. What is n cap over here? Over this, it is minus j cap. This will be minus j cap, and here will be j dot j mod divided by, and in this case it will be xy plane k dot n cap. So this will be, and here is minus k, so this will be k dot minus k cap, and this will be k dot k cap. So if we again look at the figure, so I will be in a position to explain you. Over here, this is OGFE. Where is OG? OGFE. This is only in ZY plane. So only projection is possible in ZY plane. So here we are helpless, but to write it here as dy dz. Only projection is in YZ plane. And we have substituted I dot minus I from this formula that we have drawn. Similarly, of this face, this is only two-dimensional figure, so only projection is in ZY plane. Similarly, this one, and similarly all other faces. So now, what we will do, we will write the limits for y and z. So here, if we see y over this axis, here y is 0 and here is b. So I'm going to write the limits as 0 to b. Here, since you have to keep it in mind, here y is first, so limit of y will be firstly written, and z is from, it is from 0 to c. So this will be 0 to c. Similarly, writing y, this will be 0 to b, and this will be 0 to C, and this will be 0 to A, 0 to C, this will be 0 to A, 0 to C, and this will be 0 to A, 0 to B, 0 to A, 0 to B. So this is the case. So now if we say here x is 0, so here x will be 0, x is A, here x will be A, y is 0, here y will be 0, y is b, here y will be b, z is 0, here z will be 0, z equals to c, z will be c. So I'm going to write here as x at the footstep, x is equal to 0, x is equal to a, and this will be y is equal to 0, y is equal to b, and this is z is equal to 0, z is equal to c. Now I am going to take the uh, vector field. What is the vector field given in the question? So this is the vector field given in the question. So here we know I dot I is 1 and it will be minus 1 and mode will be 1. So this will be 1 1 1 1, this will be 1, this will be 1. So here it will become 1. So f dot I cap, if I say here, what will be f dot I cap will be x square minus yz, and f vector dot minus I cap will be minus x square minus yz. Similarly, because we know that I dot I, j dot j, k dot k is equal to 1, and cross it is 0. I dot j or j dot k and any other cross is, it is 0. So this is the relation that we have used. Similarly, if I say f dot j cap will be y square minus zx, and f dot k cap will be z square minus xy minus xy. So this integral now can be written as this one, and see, we didn't change the order here. If here is dy dz, because if we change the order, then we need to change the limits. For y, limits of y are written, for this y limits of y are written, for this z limits of z are written, so we cannot change the order. So we written dy dz, and f dot I cap is f dot I cap is this one, and minus because of this, so say here is minus. Similarly, all other values are substituted. Now I am going to put next, we will put these values here in place. I will put 0, so this will be 0, it will be plus yz, so here will be a, this will be 0, and this will be b, this will be 0, this will be c, and we will get, now this we will get after substituting 0, a, y0, yb, z0, zc. So see if this integral and this integral. So one part of this part and this part will cancel out. So we may cancel this one. So this will cancel out and this portion with that only, and this portion with that, this portion with that. So ultimately we are left with 0 to c, 0 to b, a square dy dz, 0 to c, 0 to a b square dx dz plus 0 to b, 0 to a c square dx dy. Now we need to integrate it, so we will be integrating it. So this will be like 0 to c, a square will be here, this is y, from 0 to b dz plus 0 to c, it will be x, and here will be b square, and x is from 0 to a dz plus 0 to b, here will be c square, and this will be x, 0 to a, and here is dy. So if you will put a square 0 to c, this will be b dz plus b square 0 to c, this will be a dz plus c square, this will be 0 to b, this will be a dy, this is equal to a square b, and this will be 0 to c dz b square a 0 to c dz plus c square a, and this will be 0 to b dy. So this is further equal to a square b c plus b square a, this will be c, this will be c square a b, if we take a b c common, so this will be a plus b plus c. Therefore we have proved that surface integral over the surface S is equal to a b c, a plus b plus c, and we have also proved that volume integral of divergence of f over the region R is equal to a b c, a plus b. You have to prove both. Since both are equal, therefore we can write this surface integral f dot n cap ds is equal to divergence of f vector dv over region R, and this establish and verify the Gauss divergence theorem. So I hope you will be able to understand this topic. This is very important question from the examination point of view, and all other questions will run on the same lines, and you will be able to attempt those questions. So that's all I have from this lecture, and if you have liked the lecture, please like, subscribe, share and comment. This is Dr. Rajesh saying you goodbye, take care, bye bye, and see you soon. Thank you very much.